So we'll do the river boat problems. In all these problems, first there is a river which is flowing with a velocity u. This is the direction in which the river is flowing. Here there is a point A, and directly on the other side of the bank there is a point B. Let us say for now the width of the river is d. There is a person who can swim in still water with a speed of v. V is person's speed in still water. Sometimes books also say this as person's speed with respect to water. The same thing can also be said in different way. Person's speed with respect to water. How is that? How do we justify this statement with the one that I am saying here? Let's see. Or rather I should use the term here velocity. That is more precise. So I will use the term velocity instead of speed, because I can always point out the direction. See, actually person's speed in still water or person's velocity in still water is v. Let us say he is going in this direction with a velocity v. If river is also flowing, his net velocity will be person's velocity plus river's velocity. Okay? Or suppose, I will give a more simplistic example. If he is flowing to the right with speed v, suppose if the river is also flowing with speed u, we saw his net speed will be, or net velocity will be v plus u in that direction. This is the velocity of the person with respect to ground. Now, what is the velocity with respect to river? That means I am assuming river is at rest. With respect to river means river is the observer now. River observes. So I must bring river to rest. How do I bring it to rest? By adding a negative velocity u. So to this add a negative velocity u. So u gets cancelled, v remains. So person's velocity in still water is same as person's velocity with respect to river. Both mean the same thing. Okay? Now with this thing in mind, we will discuss what is the problem here. So person's speed in still water is v. Person's river speed is u. Now there are many cases. First we will discuss everything under the case v greater than u. Person's speed is more than river speed. Okay? Now the problem here is case A, person directly wants to reach the opposite side B, directly the opposite point B. This is case 1. So person wants to reach B. This is the first case that we are going to discuss. Case 2, person wants to reach the opposite bank, not necessarily B, but in the shortest possible time. So case 2, person wants to reach opposite bank in shortest possible time. So these are the two cases that we want to discuss. Both cases under this condition, person's speed is greater than river speed. Now, the person wants to reach directly the opposite bank. How can he do that? If he starts swimming in this direction, river will push him to the right. So he cannot reach. See, there is one very nice concept here. If there are two perpendicular directions, one I call as x direction, one I call as y direction, then you can separately apply kinematics in x direction. You can separately apply kinematics in y direction. For instance, you have the equation v equal to u plus at. It's actually a vector equation, but you sometimes write it as many scalar equations by taking components. You take components of v as vxi plus vyj plus vzk, uxi plus uyj plus uzk, and so on. And when you equate the components, you get an x equation like this. You get a y equation like this, and so on. See, when you write the x equation, there is no term called ay. That means y acceleration will never change x velocity. Only x component of acceleration changes x velocity. So you can separately apply kinematics in x direction, separately in y direction. I'm going to use this concept extensively in this topic. Now the person directly wants to reach B. So if he starts swimming in this direction, he cannot reach because the river will push him to the right. He is swimming this way, river is taking that way. Both are independent. Both directions are perpendicular, both are independent. So the river will take him to the right. That won't work. So rather he should swim at some angle with respect to vertical. Let us say he swims at an angle theta. Now the idea is part of his velocity will nullify the reverse velocity. So his horizontal component of velocity, which I call it as v sine theta, v cos theta is vertical component, v sine theta is horizontal component. This v sine theta must nullify the reverse velocity, must be balanced by the reverse velocity, so that when both these velocities cancel, only vertical velocity remains, he will directly reach B. So at what angle should he swim so that he has to reach B? Given by sine theta equal to u by v. So if he swims at this angle, he will directly reach the opposite bank. Okay, is that clear? So the idea is he will swim at an angle, a component of his velocity nullifies or cancels the reverse velocity, the other component will enable him to cross the river. This is the idea. So he must swim at an angle given by sine inverse u by v. Remember, u is less than v, so this is less than 1. Sine theta should be less than 1 or equal to 1 maximum. Okay, so in such a case, what is the time taken by him? Time taken by him to cross the river. So we are discussing case A, where he has to reach the opposite bank. He must swim at an angle theta given by this, and time taken by him will be given by t equal to the distance travelled d by the speed with which he is going, which is v cos theta. So this is the time. How do you know theta? You got it from here. Sine theta is given by u by v. So he must swim at that angle so that his velocity cancels reverse velocity. His horizontal component cancels reverse velocity. Vertical component will take him to the opposite side. This is the first case where he has to reach the opposite bank. Now what about the second case? In the second case, person wants to reach the opposite bank, not necessarily B. He wants to reach wherever it is, it's okay. But he wants to reach the bank in the shortest possible time. The time taken by him must be least. Now what should he do? See, there is already one expression here. One thing is we can minimize this time. How you can minimize this time? See the denominator, cos theta. Time will be minimum when denominator is maximum. When will denominator be maximum? When cos theta is 1, means theta is 0. So if he swims at 0, he will not reach B, but he will reach quickly the opposite bank. Why does he reach the opposite bank quickly? Let's try to understand this. See, his full velocity v is now directed like this. So I can draw a diagram where he starts from here, he keeps going like that. But you see, all his effort is used to kill this distance d. He is using all his effort to kill this distance d with velocity v. So his full velocity is used to kill d. Horizontally, river may take him. That's not necessary, not immaterial. We don't need to worry about that. Horizontally, the river may take him to anywhere. I don't care. My full effort must be to cross the river, which is to kill this distance d. So that is why theta is 0. So if he wants to reach the opposite bank in the shortest possible time, his velocity must be in vertical direction. Okay, so let's discuss that case now a bit in more detail. The first case is quite simple, as I told you. He will swim in this angle in such a way that his horizontal velocity is balancing the reverse component, vertical velocity is taking him there. Now let's see the second case where he will be reaching the opposite bank in shortest possible time. So I'm going to erase this figure and we'll discuss that concept. Okay, so let me erase this. So now he has to cross the river in shortest possible time. So he is directing his velocity this way. But what is the river doing in the meantime? It is pushing him to the right. So reverse velocity is this way. How is his net velocity? Net velocity is in that direction. It is given by root of v square plus u square, and net velocity makes an angle theta with horizontal. That theta is given by tan theta is v by u. From this triangle, tan theta is v by u. You see, I am treating vectors like certain lengths. That's the beauty of these vectors. Now he is actually going in this direction like that. Surprisingly, he takes the shortest possible time. You might say he is going in a long path, but this is the case where he takes the shortest possible time. Let me explain how. One way to get this time is, ultimately his net displacement is this. You take component of this displacement, vertical component. What is vertical component of this displacement? D. This is the vertical component. This is the horizontal component, total displacement. Vertical, horizontal, total. So vertical component of this displacement is d. And what is his vertical velocity? V. This gives you the time he takes to reach the river. Why does vertical component of velocity by vertical displacement by vertical velocity gives the time? Why it gives that way? Let's see. Ideally, how should I calculate time? I should calculate it by taking total displacement S by total velocity. What is total displacement? If I know d, total displacement will be d by sine theta. See, sine theta is d by s. Sine theta is d by s. So what is s? D by sine theta. Total displacement is d by sine theta. So total displacement by what is total velocity? This root v square plus u square. But root v square plus u square. But we already know tan theta is v by u. Tan theta is v by u. So what will be hypotenuse? V square plus u square. So what is sine theta from here? V by root v square plus u square is sine theta. Okay. So if you put that, what do you get? D by v only. Surprised? Total displacement by total velocity is same as vertical displacement by vertical velocity is same as horizontal displacement by horizontal velocity. So I could have simply taken this vertical displacement d by vertical velocity, which gives me the time to reach the opposite side. No need to take the total displacement by total velocity. So in order for him to reach the opposite bank in the shortest possible time, he has to swim this way. River might take him that way, but he is killing his entire distance d with full velocity, so time taken will be d by v. After all, vertical and horizontal are independent. So you need not worry. Take vertical displacement, vertical velocity, get the time. Okay. So this is the idea where he is going to the opposite bank in the shortest possible time. Now let's do a problem based on these concepts. We'll solve one problem. The problem goes like this. Exactly, we'll use all these concepts which I have discussed up till now. So there is a river of certain width. Width is not given. It could be anything. The river's velocity is 2 km per hour. Two persons start from A. Person 1 and person 2. Both persons' speed in still water is 2.5 km per hour. Both persons' speed in still water is 2.5 km per hour. Okay, or you can say this is the speed with respect to river. We saw that previously. Now, one person directly goes to B, like that. So how is he swimming? He is swimming at certain angle so that he will compensate river's velocity and remaining velocity will enable him to go there. The other person is reaching the opposite bank in the shortest possible time. So how is he swimming? He is always swimming in the perpendicular direction. He wants to reach the opposite bank in the shortest possible time. So in fact, he will reach the opposite bank in shortest time, but he is not reaching B. He is reaching some other point. Why he is reaching some other point? Because river has taken him to the right. Now from there he starts walking with certain speed v dash. It is found that both persons simultaneously reach B. This is what the problem is saying. Two persons have started, both from A. One swam directly to reach B. Other swam always perpendicular to river's direction and ultimately walked the remaining distance. But both reached the point B at the same time and we have to find V dash. This is the problem. So let's do that. First person A, he will be swimming at certain angle phi to vertical. Why? Because he has to directly reach B. Part of his velocity must cancel reverse velocity. So his velocity is 2.5. So 2.5 sine phi. Cos phi is vertical, sine phi is horizontal. Horizontal must balance reverse velocity. Is given by 2. So I must have sine phi is 20 by 25, 4 by 5. So phi is 53 degrees. Sine 53 is 4 by 5. Okay. Now, what about the time he takes? Let us take the width as d. Let us take the width as d. So time taken by him will be the width d by his vertical component, which is 2.5 cos phi. Vertical component is 2.5 cos phi. Horizontal is 2.5 sin phi. Both 2.5 sin phi and 2 have been nullified. So 2.5 cos phi will enable him to take it there. So d by 2.5. If sin phi is 4 by 5, cos phi will be 3 by 5. So it will be d by 1.5 hours, I can say, if I take d in kilometers. The other person swam always perpendicular. So time taken by him will be vertical displacement by vertical velocity. Okay. So time taken by second person in the first half, okay, first half will be vertical displacement, which is d by vertical velocity, which is 2.5, because after all he is aiming and swimming in this direction. River may take him in that direction, that's separate. Now, how far will he reach? He took this much time to reach there. In this time, what did river do? It took him horizontally. He is traveling vertically, but river also took him horizontally. So in this time, what is the distance he traveled with the help of river horizontally? So this distance BC is given by this time into river's velocity. So 2d by 2.5. That is the distance river took him. So he actually took a time of d by v, his speed, to cross the river. In that time, river did not keep quiet. It took him horizontally. So in that time, river took him with a speed of 2. So horizontal distance the river has taken him is this much. Now with this horizontal distance, he is walking back with speed v dash. So what is the time taken by him to cover this horizontal distance? Horizontal distance BC by the speed, horizontal speed v dash. BC we already calculated, 2d by 2.5 into v dash. But both are reaching at same time. So time taken by first person, d by 1.5, must be equal to the total time taken by second person. Time to reach here plus to come there. Time to reach here, we already calculated, d by 2.5 plus excuse me, time to take to cover CB, which is given by 2d by 2.5 v dash. You see, d is getting cancelled. We do not need d here. So from this equation, I can just calculate v dash. If you calculate that, let's see that it will be 1 by 1.5 minus 1 by 2.5 into 2.5 by 2. So I think it comes out, this is 1 by v dash, I'm sorry, this is 1 by v dash. So I think v dash will come out to be equal to 3. Alright. So this is how we do problems of this type. Then the last part which I want to discuss in relative velocity is the riverboat problem, which is our last and final thing. It's very simple to deal with those problems using vector diagrams. So let me discuss that with the help of vector diagrams. So in rain umbrella, this is the last model that we are going to discuss, the problems based on rain and umbrella. So what is the point here? Suppose there is a person and let us say he is going with 4 kilometers per hour and rain appears to him to fall vertically. Then he goes with, the same person starts going with 8 kilometers per hour. Now rain appears at an angle of 45 degrees to vertical. And we have to find the actual speed of rain. So let us first see. First, let us guess a direction for rain. Maybe rain was falling like this. Actual direction of rain with respect to ground. But with respect to person, rain is vertical. With what speed he is going? 4 kilometers per hour. With respect to person means what should I do? I must add negative velocity of the person. So if I add negative 4, there is a possibility that rain is vertical. You see that? This is the actual velocity of rain. With respect to person means I must add negative velocity of person, and there is a possibility that rain is vertical. Then he is going with 8 now and finds rain at an angle of 45. If he is going with 8, we must add negative 8. We already added negative 4. Add another negative 4. And this now appears to be at an angle of 45 with vertical. I could have drawn this in a different way. This is actual velocity of rain. Add negative velocity 4. Rain appears to be vertical. Add another 4. Why? Because he is going now with 8. 4 plus 4. And rain appears to him at an angle of 45 degrees to vertical. We must find actual velocity of rain. You see from this diagram, it's already quite simple. If this is 4, this is 45, this has to be 4. It's a vector diagram. You manipulate it exactly in the same way as your geometry. So if this is 45, this is also 45, sides should be equal. If this is 4, that is 4. If this is 4 and this is 4, this should be 4 root 2. You see how simple it is. So actual velocity of rain will be 4 root 2. Is that clear? So the person is actually going with 4, finds rain vertical. Person going with 8, finds rain at an angle of 45. So I took a guess. Let actual velocity of rain be this way. Why I took it that way? Why not this way? If you take it this way, if you add negative velocity of person, it cannot be vertical. So I took it that way. So if rain's velocity is this way, if you add negative velocity of person, there is a possibility that it is vertical. Add further another 4 and you see that it makes an angle of 45, which I have shown in the form of triangle law of vector addition instead of parallelogram law, because it is quite easy to visualize here. So you can do many sorts of problems. but the concept remains the same, which is add negative velocity of observer to every object in the universe and calculate. So with this, I want to conclude this really interesting topic called relative velocity. And again, let me remind you that if you have any doubts, please see your screen. On the bottom, you'll find the telephone number, and there you can call and reach us. Thank you.